Man cards, mana cards.
Y'all ready? Okay, let's get started. So there's no quiz today, but I did hand out the notes for today because the projector's still dead, so I will not hopefully have to do this all semester, but I'll refer to this today if need be. Basically what we're going to be doing is starting our first technique of integration, and the techniques that we have that we're going to study this semester are U sub, which is today, or U substitution, or substitution, however you want to call it. And then we're going to have what's called integration by parts. Which is a very interesting technique. Then 3, we're going to do trig integrals. And then we're going to do trigonometric substitution. I'm just going to call it trig sub. And then the last one is going to be partial fractions. All right. So this is just giving you kind of an idea of where we're headed. All right. Start with this one today. By far, 4 and 5 are the most time-consuming and difficult. And then I'd say if I was ranking these, integration by parts would come in then as being the next most difficult. And trig integrals, you just have to know a bunch of formulas. But yeah, that's it. So you ready? Okay, before we can begin, if you remember last class, I kept on asking, like, okay, we have a little f, can we find capital F, right? And we don't want to have to write that down over and over, like find the antiderivative of this, find the antiderivative of this. So instead what we do is we write this notation, right? I didn't show this to you, or did? No, right? Okay, so this right here, this symbol is, and this is on your notes here, is called the integral sign, all right? So this is called the integral sign. The function itself is called the what? The integrand, okay? This little dx right here is called the differential, and I will explain in more detail later what that differential is. But for us, what I want you to keep in mind is that that is telling you what the variable is in the problem. It's telling you that we want to find the antiderivative of a function where x is the independent variable. We are going to see today that this little dx can change. It can change to other things like dy or du, all right? It just tracks the variable. And then we have capital F of x, which is the antiderivative of that, right? And then we have plus c, and this is called the constant of integration. All right, so that's some new notation for us. Now, the next note here talks about the power rule, which is something we already did, right? We talked about the power rule, and we said that it was 1 over n plus 1 times x to the n plus 1, so long as n was not negative 1, and then it's natural log of the absolute value of x plus c if n is negative 1. And then there's the common formulas, and I reference what page you can look at in your book, or on your formula sheets to get those common antiderivatives. All right, so that's all from last class, 5.52 and 5.53. All right. Let's start the U substitution. I know I did a little bit at the end of class last time, but let's really get into it now. So to get us started, what I'm going to do is I'm going to give you a function. And I believe I have sine of x squared there. And I'm going to ask you a calculus 1 problem, which is to do that. What is that telling you to do? Find the derivative, right? This is saying take the derivative with respect to x of sine of x squared. So if we're going to take that derivative, what would we get? Cosine of x squared times 2x, right? And if we wanted to maybe clean it up, we could write 2x cosine of x squared. That wouldn't really do anything different other than move the 2x out front, right? All right, now let's look at this next question. The next question is to find the antiderivative, right? That's what this is saying. Find the antiderivative of x cosine of x squared dx. So this right here is the integrand. That's what we're trying to find the antiderivative of, right? Now up here, this is very close to this, right? So the antiderivative should be this, kind of, right? What we don't have is, this one had a 2, didn't it? And this one doesn't have a 2. So somehow that's gonna factor in, right? Now when we look at this antiderivative, you can't do, because it's a product, you cannot do them separately, right? You have to somehow put it all together and kind of reverse or undo this chain rule, right? Because that came from a chain rule. We're going to try and undo that chain rule now. Yes?
So you said that symbol is antiderivative of that.
This is telling you to find the antiderivative of this. Instead of me writing down, find the antiderivative of this, I just write this symbol with this, and then the dx is tracking our variable. Got it? All right, so let's see, how are we going to go back? This is just to show you kind of where it came from, all right? So what's the technique? Because today is about a technique, and I have it 5.5.5. I want you to look at that. The technique says that we are going to look at the integrand, all right? We're going to look at the integrand, right? We're going to look at it. And what we're going to look for is, number 2, we're going to try and find something in there, and we also want to see its derivative in there somewhere, all right? Now what I mean by that is, since this is our first example, I see something in here, x squared, right? And its derivative is 2x. And I almost have 2x out here, don't I? I have x, not 2x. So look at number 3. It says the derivative should appear in the numerator and not be trapped. So this is the derivative, right? Is it in the numerator? Yes. Is it trapped? What I mean by trapped is it underneath the root? Is it inside of a function? Like it's not sitting inside of a cosine, or it's not sitting inside of a natural log or anything, right? It's kind of isolated by itself. In other words, you could write it like this. Right? It's kind of all by itself on its own, right? You need that for this technique to work. I see something, I see its derivative, right? Okay. Now, there's a part 4. The derivative might be off by a constant. That's good, because the derivative of this was what? 2x, and this is just x. I'm off by a constant. According to this technique, that is okay, all right? So long as this is not in the denominator, so long as it's not trapped inside of a function, and so long as it's only off by a constant, I can proceed to the next step, which is part 5. Let u be that something that you saw, all right? So what am I going to call u? X squared, all right. So this right here is the something, right, that I tried to identify. So I'm making a substitution. I'm changing, anywhere I see x squared, I'm going to replace it with u, right? That means if we rewrite this right now, this is going to become cosine u, isn't it? But then I'm going to have x dx over here, and the idea is to not have x's and u's mixed together. It's either going to be all x's or all u's, one or the other. Can't be both variables at the same time. So that means I need to somehow make the x dx become something with u's in it, right? So here's what I do. I go back to this, and I take the derivative implicitly with respect to x. So that means I'm going to take the derivative of the left side of this. What is the derivative of u with respect to x? Du dx, right? And then the right side, what's the derivative of x squared? 2x. Okay. Now we're going to play this little matching game. I'm going to try and somehow create x dx out of this equation. Is there any way that I can manipulate this equation to get x dx by itself on one side? So just algebra, just doing algebra. Multiply both sides by dx, okay? If I multiply both sides by dx, I get this, don't I? Dx cancels here and appears here. And then divide both sides by 2. Or if you'd like, I prefer to look at it as multiplying by a half. So multiply this by a half, multiply this by a half, and voila, look what I have over here, x dx, right? So what I have now is I have a way of replacing x squared in the problem, right, with u. And I have a way of replacing x dx in the problem with something that just has u's in it, right? So let's see what we get. Let's rewrite the integral. We still want to find the antiderivative, but instead of this, we want, you tell me, cosine u, and then times, what's x dx? 1/2 du. Now that 1/2, I can pull out to the front. In fact, I could put it right in front of the cosine, couldn't I? But isn't it always just going to come for the ride anyway? It's just going to be with us. So why don't I pull it all the way out of the integral and look at that as being, I'm going to take 1/2 and multiply times whatever I get here, cosine u du. Y'all still there? Okay, so look, if I would have walked in today and handed you a quiz and I said, hey everyone, well, I couldn't have used the integral sign, could I? But if I would have asked you what the antiderivative of cosine of x was, everyone here would have said sine of x? So if I'm asking you what's the antiderivative of cosine of u, you're going to say sine u, right? Plus a constant. But we have a 1/2 out front too. So we have 1/2, then we have sine of u plus some constant. Now we're not done. Why aren't we done? Because we still have u's, right? That's like me asking you what your favorite color is, and you say Ford's, or it's just like doesn't make any sense, right? Like we're asking you what's the antiderivative in terms of x, and you're talking about u. It's like that doesn't make sense, right? So get it back to x, and that's no big deal because I know what u is, don't I? U was x squared plus a constant. Box it up. And what was always the good news about this? That you can check it by taking the derivative, right? So the 1/2, if we take the derivative, the 1/2 is going to stay here. I'll just do the derivative right here. 1/2 is going to stay here. Derivative of sine of something is cosine of it, times derivative of what's inside, which is 2x. The 2's cancel, and what are you left with? Cosine x squared times x, and that's exactly what the integrand was, right? So we were able to take care of that too, right, by scaling by a half. This is the way substitution works. You look at the integrand, you try and find something in its derivative, you make a substitution, you try and get this thing to match up. Oh, I erased it, but you try and get that dx-y thing to match up with this, and then once you get that, you rewrite the problem. Hopefully, what you see now can be integrated easily. All right. Let's do another one. All right, now, before substitution, the only real way we could do antiderivatives was the power rule, right? Which means we had to have x's to the powers, or it had to be something we recognized from Cal 1. Other than that, we didn't have anything, right? So if I'm looking at this integral, the first thing I'm going to do is see, can I do this with a power rule? Can I split it up where I get just powers of x's? No, because you have 3 terms in the denominator. And so there's no way that you can split it up and just get x to a power, x to a power, x to a power, right? So then I go through my little Rolodex of techniques and I say, okay, u sub, maybe I can try that. So I'm looking for something in its derivative. Do you see something in its derivative? Okay, so who wants to volunteer what they see?
Bx squared plus 4x plus 1
This whole thing on the bottom? What's the derivative of that? It's what's on top. Right? This is example 2, so I'm making this pretty obvious. The derivative of this is up here, right? Now, could I have just done that? What's the derivative of just this? Same thing, right? So there's like this kind of a delicate balance that we have to find here. We want to choose a u that gets us what we want, right? We need to choose enough that we get this up here, right? But we don't want to choose too much, right? We don't want to grab too much. You'll see in the next example what I mean by that. But if I let u be x squared plus 4x plus 1, if I grab the 1 also, then the derivative of it is still this, right? Yeah. So I might as well grab as much as I can without going overboard. So I'm going to put the 1 there. Got it? Now what? Differentiate, right? Du dx. That's going to be the standard practice on all these problems. Once you choose u, next step is du dx. Take the derivative, 2x plus 4. I'm also going to put this in parentheses because of my next step. What am I going to do on my next step? Get the dx out of here, right? So du is 2x plus 4 dx. That's always going to be the standard technique also, to clear that dx out. Now, over here on this problem, I want to make sure that you understand that this is really the same thing, right? Like that numerator can just kind of be peeled off the top and just placed over here with multiplication. And it's helpful to see that because we're trying to match things up. We already know we're going to call that u, right? And so all we really need to do is figure out, how we can replace this. And look at that. It's there, right? I mean, it's right there staring at you, just looking at you. I'm right here. You don't even have to do anything to me, right? So what should we do next? Just rewrite everything, right? So this integral becomes integral 1 over u, right? And then all of this is exactly du. And so just go back to, again, if I walked into class today and I said, hey everyone, what's the antiderivative of 1 over x? You would have told me natural log x, right? But it's 1 over u. So the antiderivative should be natural log of u. And I want you to start doing something. When you do the antiderivative of 1 over u or 1 over x, put the u or the x in absolute value. And that just helps us with the domain restrictions that we have on natural log. You can't plug negatives in. So this avoids any sort of issues later. And then I'm missing something here. Plus c. And then now rewrite that in terms of x, not u. So x squared plus 4x plus 1 plus c. That's it. That's your answer. Yes?
Sorry, where does absolute value come from?
It comes, the formula, if you look on the sheet, the notes I have, it says on here that it's 5.5.2. The antiderivative of x to the n is natural log of the absolute value of x plus c. Now, why it's that way is the fact that you can't plug a negative into a natural log. So we put the absolute value so that we eliminate any sort of issues that we might have. Like, what if x was negative here? Like, what if x was negative? Then you could potentially get a negative inside this log. So if you put absolute value, then you don't have to worry about that. Mm-hmm. All right. What do y'all think so far? I make it look easy. I mean, are you following? Okay. Let's see if we can do something. How about this? Okay. How about 4x minus 8 over x squared minus 4x plus 3 cubed dx. Now let's do something that I might do several times this semester. Let's just take one step back and appreciate how complicated this thing looks to start now. I mean, all I've done is introduce U substitution, right? And all of a sudden I'm giving you these things that look a lot worse than the things we were doing last class, right? And that's what happens with every technique we look at. The scope of the type of integral we can see becomes that much more. But this one is well within the ability that we have here with U substitution. So do you see something in its derivative? So if we choose this to be U again, right? What's its derivative? Let me just write it down. U is equal to 2x minus 4, right? Okay. No, why did I put 2x? X squared. I'm already taking the derivative, sorry. What the hell, Robert? Okay, there. That's what U is. I was already taking the derivative. That's what U is, right? Then what's its derivative? 2x minus 4, right? Yeah. And if I bring the dx to the other side, I multiply, I get 2x minus 4 dx. So I took the derivative, then I brought the dx to the other side. From here on out, I'm going to skip this step, and I'm going to go straight to this. So I'm going to take the derivative, and then I'm just going to slap a dx on the outside, all right? Because that step just isn't necessary. Now, do we see this? Do we see this in there? Or is something, let me see, maybe we can, how about we do this again? Let's kind of peel it apart so we can kind of investigate it a little bit more. Okay, so you can look at this two different ways right now. This is not exactly this, right? What I could do, though, is I could multiply this by 2 and this by 2, and I would get it, right? Yeah. The other thing you could do is you could say, hey, here I have a common factor, right? And I could pull a 2 out. I understand I could pull a 4 out, but I wouldn't want to pull a 4 out, right? Because then it wouldn't match this. So I could take a 2 out of this and pull that 2 out here and then put it on the outside because the 2 would just come along. So it's your choice. I don't care which way you do it. How about just for this example, we realize that we almost have this here. I just need to multiply 2 here and 2 here, right? And now we have 2 du is equal to 4x minus 8 dx. Now it matches, doesn't it? This matches exactly with this. My new integral becomes what? This was supposed to be cubed. I don't know why I put squared there. That's cubed. Okay, so you want the 2 out now? So I'm going to do it on the next step, okay? I've got 1 over, right? 1 over, and then this right here was u, so u cubed. And then all of this in red here became this, or was this, so it becomes 2 du. And what you're saying is you can take that 2 and just pull it all the way out, which I'll do on the next step. So I have 2 integral, now 1 over u cubed. What am I going to use to integrate that? How do you integrate 1 over u cubed? Power rule. You first need to write it as u to the negative 3, then du, right? Then you can use the power rule. This is like x to the n. Just we're using u's instead of x's. So 2, now no more integral sign because I'm taking the antiderivative. According to the formula for this, it'll be 1 over negative 3 plus 1 u to the negative 3 plus 1 plus c. So that's the formula from last class, right? You see how you got to know how to do the power rule, or else you can't do this problem, right? You still need that from last time. So this is 2 times, what's this here? This is 1 over negative 2, right? So negative 1/2, u to the negative 2 plus c. And what happens out front there? 2's cancel, so I just get negative, right? Negative 1 times, how about I write that as 1 over u squared plus c. So that's negative 1, this is 1 over u squared plus c, and I'm almost done. I just need to replace my u with what it is. And u was what? It was x squared minus 4x plus 3. So how about I write it like this? Negative 1 over x squared minus 4x plus 3, that quantity squared plus c. So that is basically the negative coming up here, and then me rewriting u with what it was, and then squaring it, and then putting plus c at the end. There it is. That's the antiderivative. Y'all still feel all right? Okay. So the technique that I'm using here is, I mean, all the problems we do is it's going to require this technique, right? It's just going to be a little bit harder to see sometimes what the substitution is. So let me start to crank it up a little bit.
So if we just leave the answer like that, like in a test or something, if we just leave the answer like that, like negative 1 times
1 over,
yeah, like,
as long as you replace that with what u is, it's good. You just can't leave it as u though.
okay.
Because that's like, again, me asking you your favorite color and you give me the model of a car.
Well, as long as we don't, I mean, if it's a product like that, like negative 1 times, like, is that fine?
That's fine, yeah. But also understand that that negative 1 can just slide up top. Yeah, okay. All right, let's try this one. Are y'all ready? I'm going to turn the screws a little bit now. So, have y'all heard that figure of speech before? Turning the screws? I think I know what it comes from, but I could be wrong here. I believe that back in the medieval days there was a torture device where they would like put your head in like this vice, and then they would start to turn the screw and you know, admit that you're wrong, or you know, tell us the secret password, and they turn the screws, just get a little more, and just enough until you either died or you gave up the goods, whatever. Okay, so I'm going to turn the screws now, and I think this one's going to be appropriately messy, but let's just see what happens. I'm a little bit concerned. If you like solving problems and puzzles and stuff, that's kind of what we're doing here. We're trying to like squeeze something out of this. We know it's there. Like I wouldn't give you this problem if u substitution didn't work, okay? But it's your job to find the path. What's the appropriate u here? I told y'all I hated baseball, right?
Yeah.
Yeah? But I still got up and took swings, right?
What if you like use the Pythagorean identity?
Mm-hmm.
Cosine?
You could do that. Like you would have to change cosine squared into 1 minus sine squared. That would be fair. That would be fine. Now, do you think you would gain anything with that? Let me just write it down here. Because if you're thinking that, then you perhaps want to consider like what it looks like and is it any better? Like, did you gain anything there? Do you see something in its derivative there? I still don't see something in its derivative there.
Was there a Calc 1 what do you call it? Derivative of Pythagorean identities, or that's not that gave you cosine 2x? Is there a derivative that gave you that?
I don't believe that there is a derivative that in Cal 1 that you should know that would give you cosine squared x.
Can't remember.
Well, we know tangent, derivative of tangent to secant squared x, but that's whatever.
Okay, so wait a minute. It sounds like you just took a swing with u being tangent. Is that right? But the derivative of tangent is secant squared.
And secant squared is 1 over cosine, or 1 over cosine squared.
Yeah, so wait a minute. What's that relationship? Okay, hold on. Cosine of x is 1 over secant x, isn't it? Yes?
That's what I'm saying.
So what would cosine squared be? 1 over secant squared? Yes? So I could rewrite this, couldn't I? This cosine squared is 1 over secant squared? Yes? Okay. This is going to be we'll see how it goes. Let me just see if you believe this or not. Do you believe that? Is that the same thing?
Yep.
Okay. But we just said that we could rewrite cosine squared x as 1 over secant squared x? Okay, good. Hold on. All right, do you agree with that? Now, all of this is being done because it was brought to my attention that someone remembered that the derivative of tangent to x is secant squared x. And I'm assuming that you remembered that secant and cosine are somehow connected, right? So yes, based on the idea that the derivative of tangent is secant squared, and the fact that I have a cosine squared, which is some sort of secant squared, that maybe this will work this way, right? Maybe? Maybe? Let's try it, all right? Let's try it. So I'm going to now take the swing. U is equal to tangent x. Should I grab the plus 2? Why not, right? Does it change anything in terms of the derivative? No. Plus 2. Let me grab that. All right. So now, take the derivative. I would normally write du dx, right? And then I'm going to bring the dx to the other side. The derivative of that is secant squared x dx. Yes? We have a problem. Okay, yes. So and that's what you were saying also. I'm going to be able to replace that with u, right? And then if you squint your eyes, you'll realize that's just going to be 1 over u in the new integral. And I know the antiderivative of 1 over u is just natural log, all right? So far things look good. The problem is secant squared right here is in the denominator, isn't it? And the dx is up in the numerator. Like you can look at this as being dx over 1. So here, I don't have that. I have secant squared times dx. I need this secant squared on the bottom. But I can't just, if I divide through, watch what happens. If I divide through by secant squared x, it goes away, right? And that's not what I want. I want it to be on the bottom. So I told you in step 3 that the derivative must not be in the denominator and can't be trapped, right? And in this case, it is. So what does that mean? That means that that doesn't work, okay? That this substitution doesn't work. That's why I wanted to show you this example. Now, you probably want to know what the answer is to this, though, right? The problem is we don't have a technique right now that we can do, that we can actually handle this. So I've given you a problem that we can't solve. However, the whole point of it is for me to ask you what I could do, how could I rewrite this problem so it would work with this substitution? What would I need to do to make this problem work with that substitution? So do you all agree? We're going to say question, don't know, this technique fails. Yes? So if I asked you to write a new problem that has all of these things in it, what could I do to make this substitution work? Have the cosine squared x on the bottom instead of on the top. Then it would work, right? So look at this. New integral. What if I wrote this? Now you look at that, and when you initially look at that, you throw up a little bit, and then you kind of take one step back, and you're like, I'm looking for something in its derivative. The derivative of tangent is secant squared. I don't have secant. Oh, I do have secant squared. You see that? I do have secant squared. It's right there, 1 over cosine squared.
So would that be the same as 1 over cosine squared x and then 1 over 2 cosine x?
Oh, yes. Okay, so if I rewrote this, I would rewrite it like this. I think that's what you're asking. Yes. This is this, right? So if I let u be this, the derivative of it is this. Exactly, isn't it? This is exactly the derivative of tangent.
So wouldn't that have to be in parentheses though?
This thing?
No, the whole,
This?
both.
These?
Like,
The whole thing?
yes, except for the x. The x has to multiply both.
No, because it's multiplication, not addition. This dx applies to all of them, right? It's like, you know, if I write 4 times 3 times 2, this 2 does not distribute to both the 4 and the 3, right? If it was 4 plus 3, then I would need parentheses. I don't know if that makes sense. You only have distribution when you have multiplication over addition or subtraction. Then you have distribution. If you just have a bunch of things being multiplied, then there is no such thing as distribution. All right, so the reason I wanted to give you this problem is I wanted to illustrate with this problem that, look, that number 3 part in the technique, you have to have the derivative not trapped or not in the denominator, okay? But from what we investigated, I wanted you to kind of see how you could tweak the integral to make it work, right? Then break it apart and let's make this substitution right here. Here's our derivative, and this means this, right? Secant squared x is the same as 1 over cosine squared x. And now look at this. All of this matches that. So I'm going to replace everything there with du, right? And the other part is just 1 over u. So this integral becomes integral 1 over u du. And what's the antiderivative of that? Natural log absolute value u plus c. But then what was u? Every time I say that, what was u, it seems like it's like bad English. What was u? Okay. Yes? All right. I want to, I'm going to give you a problem similar to this one. Similar. But I have some serious doubts about whether or not we're going to see it. Look, and it's not like I'm giving you this problem because I'm trying to punish you or abuse you, but you have to see these things first time. Like somebody showed them to me first time, you have to see it first time because then you just know kind of a little more about the game we're playing, all right? Let's try this one. This one's hard to see.
One plus x is outside the confines of the square root. Oh, it's still in the denominator.
This is in the denominator, yes. And this is in a root and it's in the denominator, right?
I was thinking we could probably manipulate that, changing it to u, but it's, the left is trapped in the other.
Yep. So step up. Look, I told you last class you're going to fail more times than you succeed with these, right? Okay, so you've got to be willing to just try something for you. I mean, right now I'm looking for something in its derivative and I'm having some trouble, right? Like, if I choose this to be u, what's the derivative of the square root of something? 1 over 2 square roots of that something or something like that? If I choose x to be u, then the derivative is just 1, right? Which I already have 1, right? That might work. If I choose 1 plus x, the derivative of that is still 1, and I have that, right? But then I have a root x too, and come on, let's just take it. Just somebody give me something.
So can you just multiply the bottom times, can you just square the bottom?
Ah, thank you. I'm glad that you said that. You cannot, this, because people will do this. They're trying to make it look better, right? So they'll square the top and bottom maybe, or square the whole thing. You just can't do that, and here's why. It's like, look, if I tell you, hey, look, I have the number 4, right? If I square it, is it still 4? No. Now, if I tell you x is 4, then you can square both sides, can't you? If I square both sides here, I get x squared is 16. So you still are maintaining the relationship that x is 4 here, even after you squared both sides. Here we don't have an equation. We don't have equality. We can't square anything because it's an expression. We have an expression. When you square it, it no longer is what it was. All right? So we can't use that algebra. Sorry.
Can we multiply the bottom out?
Can you multiply this through? Yeah, you can do that. I'll put it here just so we can see it. I actually was going to present you the problem this way, but I decided not to because I thought it would be even more difficult. So I did not. I originally was going to give you the problem like that, but I decided that I would factor.
The x and the square root of x are both the same.
The
Because the square root of x is x to the 1/2, and x is x to the
So I could put that as like x to the 3/2? Yeah, I could. So I could have actually written it this way also. I definitely, just for a fraction of a second, thought of doing it this way. But that would have been even more brutal, I think, to give it to you that way. But that is what it is. All of these expressions are exactly the same, right? Okay. Nobody's willing to take a swing at it. What I mean is, give me a u. I mean, somebody's got to give me a u here.
I'm not thinking about putting the 1 plus x in the numerator, but making it to the negative 1 power, and then taking the derivative.
Why do you want to put it in the numerator?
Wow.
It's the derivative that can't be in the denominator.
Well,
Okay?
I'm saying make it like, since it's since the equation is technically like 1 over the square root of x and times 1 over 1 plus x. I'm saying make 1 plus x to the negative 1,
Mm-hmm.
and then I don't know.
Yeah, you could.
Try something like that.
Okay, let's try this. Can we just let u be x plus 1?
Yeah.
Okay, let's just try that. Let's just try this and let's just see if anything happens good. All right? What's du then? 1 dx, right? Okay. You all right with that? All right, if we try and rewrite the problem, x plus 1, that's going to be u, right? What's du going to become? What's dx going to become? du, right? So far, what's in blue is going to be converted over to u, stuff with u's, right? The only problem I have is that root x. I need to somehow get that in terms of u. Nope. I'm asking you to look at that. And I'm asking you to understand that that's the same as this, right? Just move the 1 over, subtract 1 on both sides, and then I'm asking you to take the square root on both sides. And now don't we have an equation for root x? Yes? Y'all following me? So let's see what happens. We have integral 1 over. Now, what is root x? Square root of u minus 1. Okay, times, now what was 1 plus x? U. And then what's dx? du. And when you look at that, you should still be stuck. Because that did not make life any better. Like, we still have a pretty nasty looking thing here. I still look at this like this is definitely not something where I go, oh yeah, I just use power rule. Can't do it. This is not something I know, right? It's not like cosine, right? This is still a mess. I would argue it's just as ugly as this almost, right? This had a root and it had something nice. This has a root and it has something nice, but it's still bad. So guess what? Crumble it up, throw it away. Well, maybe not throw it away. It'd probably be good to keep it and just say, hey, this didn't work, and go and start a new page. All right? This u does not appear to have done the job. Sorry to disappoint you. What's that?
Can we try to square root of x?
Yeah, we can try it. You might be leading us on a crazy path, but let's try it. All right, if u is the square root of x, then what's the derivative of this? 1 over 2 root x dx. Are we all comfortable with that?
I never even looks worse.
This looks bad. This is the right u. This is the right u. But you got to see it over there. Okay. I have a 1 over 2. Who cares about the 2? I can always get rid of that, right? I can multiply both sides by 2. So I really have a 1 over root x dx. Do you see a 1 over root x dx over here? I see it. Let's see. Maybe if I rewrite it this way, you'll see it. Yes? You see it now? That's the original problem. Just kind of multiplication. I can just kind of peel this out to the back with the 1. This is all the same, right?
We can mess with it. We can square both sides of the u.
Okay. So this right here is almost here, right? I'm going to just multiply both sides by 2. Yeah? All right. So I can replace this with 2 du. So I'm happy about that, right? This is going to become 2 du. I just need to figure out what the heck this is going to become. So 1 over 1 plus x. I don't have anything over here that has x. But I can square both sides there. And if I square both sides, what do I get? U squared is x, right? So what does this integral become then? 1 over 1 plus what? U squared, which is arctan. Antiderivative of that's arctan, right? Times what? 2 du, right? 2 du. Bring the 2 out. 2 du. Beautiful. There it is. Did it work? I mean, does that work? Do you follow it? Freddie, right? Okay. Freddie took a swing with root x. And I almost laughed at him initially going, yeah, right, Freddie. But it worked, right? It worked. Now, let's finish it, sorry. 2, what? Tangent inverse of of u, right, of u plus c. But then that's 2 arctangent of, now don't forget, what was u? It was root x, right? So root x plus c. And the good news is you can check it, right? You can take its derivative. And if you take its derivative, you should get back this. All right. That was almost fun.
And you don't have to erase the answers?
I'm not going to erase the answer. So now that we've done this problem, when you look at that original problem, you should have a slightly different perspective on it than you did when we first looked at it. You should see that you have a root x on the bottom, and then you should be thinking, hey, the derivative of root x has a root x on the bottom, doesn't it? So maybe I can let u be root x. But then what's this? Oh, but that's root x squared. So I would have like, this part's the derivative, and this is going to be 1 over 1 plus the u squared. It's arctan. I mean, that's going to take time for you to get to that comfort level. But now with that perspective, that after we've worked through it, you know, you're just kind of notching up, opening up your vision, your field of view is starting to become a little broader, hopefully. Do you see what I mean, though, when I say that, like, if you still are having trouble with the fact that the derivative of the square root of x is 1 over 2 root x, this is going to be tough, right? It's going to be tough to go backwards. All right. You want another one? Of course you do. Of course you do. Now, in the homework, they kind of slowly crank up the level. So you're going to have a lot of, like the first 6 problems in the homework section, they tell you what u is. They say, hey, use this u, and then they let you work it out. And then the rest of them, they don't tell you what u is. So let's try something similar to that one, to really see if your vision has opened up a little bit. I wish that we had time in this class for me to say, okay, now I'm going to give you 5 problems. You work on them. I'll come around and help you. I wish we had time for that. We don't. But that's why you do your homework, and that's why I have the solutions out there for you. You go sit down, you do those practice problems. If you need help, you look at the video, you call me, you text me, you come into my office, whatever, right? Unfortunately, there's just too much information in this class for us to have a bunch of group time, all right? Knowing what you know now from the last problem, do you have a good candidate for you? Root x, right? Because the derivative of root x has a root x in the bottom, and there it is, right? I mean, it's there. You're going to be off by a little bit, right? You're going to be off by 2, a factor of 2. So maybe it'll help you, before you start, to just peel that 1 over root x off to the side, like that. And then make your substitution. Root x, you say. And then du is 1 over 2 root x dx. And multiply both sides by 2. And every piece I need is there, isn't it? So what is the new integral in terms of u? Secant squared u times 2 du. 2 is going to come out. And the antiderivative of secant squared is good for us, is tangent, right? So later on, when we do more complicated problems, when we get into these other techniques, a lot of times you have to do a u substitution first to get it to look like something that then we use a different technique on. So it's like 2 things in one, and it can become a little problematic. But I would venture to say fun at the same time. Wait, what am I doing, arctangent? What am I doing? Tangent u plus c, which is 2 tan root x plus c. Awesome.
But the answer could have arc tangents or arc sine or arc.
It could. Is that? Are you asking me? Can it? Oh, absolutely. Yep. Absolutely. How about this one? 1 over x root 1 minus natural log x squared dx. It kind of sucks because I think I've already done all the homework solutions for every problem in this section. So like I can't pick problems out of the section to do because I've already done them on video, so I'm having to make these up as I go. Does anybody see something in its derivative anywhere? The natural log of x is the u, is that what you're saying? And its derivative is what? 1 over x? Oh, I see the 1 over x. You see the 1 over x? Okay, so let's try that. Let me rewrite this as 1 over square root of 1 minus the natural log of x squared, then times 1 over x dx. You're telling me to make a substitution. U is natural log x. The derivative of that is 1 over x dx. I have that exactly right here, right? That's it exactly. And so I can rewrite the problem.
Can you bring the 1 minus if you wanted to?
Can I bring the 1 minus?
Yes.
Very good question. The question that's being asked is that could we have made it 1 minus the natural log of x squared instead?
Well, yeah.
You have to bring the squared. If you're going to bring the 1, you have to bring the squared because you can't just ignore that and just bring that because the squared is acting on that, right? Do you see why this wouldn't work though? Because if you take derivative, you have chain rule. You'll have 2 come out first, then natural log, then the 1 over x. And that's way more than you have over here. What is the new integral? 1 over what? Square root of 1 minus u squared. And then this is exactly du, isn't it? Oh crap, that still looks complicated. Or does it? That's one of the ones that you need to kind of remember. That's arc sine. You asked, right? No, you asked, can it have arc sine? I deliver. There it is. There it is. Arc sine of u. You wanted it, I provided it for you. There you go. There's an example where you get an arc sine as an answer. Just say the word. I shall provide. No. I'm ready for the weekend, sorry. All right, here we go. Replace u with natural log x, and that's it. So you have to recognize this as a formula. We covered the derivatives of the inverse trig functions, and I told you that there were 2 that you should, well, arctan I told you had to know, right? Arcsine comes up pretty often also, but not as much as arctan. Arctan comes up a lot. I've heard people say that there's no such thing as a silly question, but I don't believe that. There are silly questions.
You have the DU right there.
Have a what?
The DU.
What about it?
Yeah, where's it go?
Okay. So this, yeah, that's a good question. It's not silly at all.